Okay, so let us get started. So, what we will do today is we will just finish the parity lower bound proof, and we will look at some extensions of this result, and then I plan to discuss some bit of communication complexity. Okay. So, by itself communication complexity is a very vast area, okay, and probably it needs a course by itself to completely understand the techniques and the power of communication complexity, but we will just give a brief overlook as to what the model is and what kind of problems we expect to get solved using that model. So, what we had last time were these two lemmas, right. So, we had that suppose if we have an AC 0 circuit. So, lemma 1 said that if we have an AC 0 circuit, okay, so it can be approximated well in some sense, in the sense that it can be approximated by a proper polynomial p, okay, such that degree of p is what was the degree that we had? 2 t to the power d, right. So, this was for all t, and p matched the value of this AC 0 circuit on at least size of C times 2 to the power n minus t inputs, right. So, this was the first lemma that we had, and the second lemma was, so this was lemma 1, and the second lemma was that if there is a root n degree polynomial, if there is a root n degree proper polynomial that approximates parity, then it cannot agree with parity on more than what was the bound that we had? 9/10 of 2 to the power n, right. Okay. So, P agrees with parity, where degree of P is less than root n. So, this is what we had. So, now it is easy to combine these two lemmas. So, what we do is we just set t equal to half of n to the power 1 over 2 d. Okay. Yes. We never had such a constraint, no, for any t greater than 0. There are 2 to the power n inputs, yes. So, if that is true, but all we are saying is that the number of inputs are, so what is this? So, this is basically the, so C agrees with P on so many inputs, on at least so many inputs. Okay. So, of course, I mean C cannot agree with P on more than 2 to the power n inputs, because that is the upper bound, but this is what all we are saying is that this is just a lower bound. So, t can be any number, any positive integer. Okay. So, if we set t to be equal to this, then what do we get here? We get that okay. So, let d be the set of inputs on which C agrees with P, then what we have is that cardinality of D is greater than size of C times 2 to the power n minus half of n to the power 1 over 2 D, and degree of P is less than or equal to, just if I plug in this number here, we get that this is less than or equal to n to the power half in lemma 1. Okay. And from lemma 2 what we have is that if we do have such a thing, we have that this is less than or equal to 9/10 of 2 to the power n. So, if we just combine these two equations, what we get is size of C. So, did I make a mistake? Huh? What? Which one? No, so, D is the set of points where the two things agree. So, lemma 1 says that if we have a AC 0 circuit, then it agrees on at least so many points, and lemma 2 says that P agrees with parity on at most so many inputs. In the second condition, what is the lemma 1? Oh, okay. Okay. It differs from C on this. So, P agrees with P on 2 to the power n minus that. So, okay. C differs with P on at most so many inputs. Okay. And here what we have is, so let D be the set of points where C and P differ, then we have that D is less than or equal to this quantity, and again let us keep the same thing. So, P differs with parity on at least 1/10 fraction, right. So, now I think it is correct. Yeah. So, this is what actually I wanted. So, now I can just club these two together, and we have that size of C is greater than or equal to whatever constant it is, 1/10 of. So, 2 to the power n, 2 to the power n cancels off. So, what we have is 2 to the power half n to the power 1 over 2 d. Okay. And this is what theorem 1 or the first theorem, whatever it was, had claimed. So, is this clear to everybody? So, I was just confusing with the number of points on which it is same with what was actually stated in that lemma. Okay, so that is the proof. So, now the question is that what we have is that AC 0 circuits are not able to compute a function which is as simple as the parity function. Okay. So, what if I append an AC 0 circuit with gates, okay, which does compute the parity function for us. Okay. So, let us say that I define a mod 2 gate, okay, as one that just outputs the following value. So, if the mod 2 gate is given inputs x 1 to x n, it will just output sigma x I mod 2, okay. And we can also generalize this. So, suppose if I append an AC 0 circuit, that is what I mean is that together with AND, OR and NOT gates, it can also have these mod 2 kind of gates. So, then what kind of power does these circuits have? So, there is a name to this also. So, this is known as a CC 0, and in square brackets this 2 means that it has mod 2 gates. So, then again what can be shown just by an extension of this argument is that this kind of circuits cannot compute the mod 3 function. Okay. So, mod 3 function is that given x 1 to x n, I will output a 0 if the sum is divisible by 3, and I will output a 1 otherwise. So, if the sum is not divisible by 3, I will output a 1, and this can actually easily be shown. In fact, the proof that is given in your book is actually for this particular statement. Okay. So, what we had showed was that there is a proper polynomial which can approximate the NOT and the OR gates, but you can also show that there is another proper polynomial which can approximate a mod 2 gate very easily. Okay. So, therefore, there is a proper polynomial which approximates a circuit of this form, and then on the other hand you show that now if I try to compute mod 3, that is not possible by such a kind of circuits. So, and this entire thing can be generalized to the following. So, suppose P and Q are distinct primes. Okay. So, they are not the same, then the mod P function cannot be computed by an ACC 0 circuit with mod Q gates. Okay. So, this additional C just stands for counter. Okay. So, it is a constant depth, polynomial size, unbounded fan-in circuit together with mod Q gates. Okay. So, that is what it stands for. So, this is the general theorem which actually Rasborov and Smolensky proved. Huh? So, you are saying that you have one ACC 0 circuit which has all the primes up to some k. Yeah, so that is the thing. So, suppose if you have a ACC 0 circuit, forget about k. suppose it has two kinds of gates, suppose it has mod 2 and mod 3 gates. Okay. So, suppose if we allow it something like this. So, it is denoted by ACC 0 and let us say it has mod 2 gates and it has mod 3 gates. So, what is the power of this circuit? So, this was an open question which came up immediately after this result. Okay. So, this was for a single prime and people started asking that can I show that certain functions are not possible. So, people failed, I mean it was not possible to show some easy functions cannot be computed by this circuit. So, they tried to see that can I show some p complete problem that is not being computed by this circuit. So, that was also not possible. People failed even for NP. So, even if you took an NP complete problem, they are not able to show that NP complete problem was not being computed by such a circuit, and this went all the way up to NEXP. Okay. So, it was an open question whether there exists a language in NEXP. NEXP is a very powerful class such that L does not have an ACC 0 circuit of this form. Okay. So, this was the open question. Does there exist a language in NEXP? Okay. And after this result, so this was in the late 80s, after this result up to last year, in fact this was an open problem, and it was just last year by a guy named Ryan Williams that it was showed that there is a language in NEXP which does not have ACC 0 circuits. Okay. So, yeah, so now this problem is solved and it is a very recent result. So, you can see that a very simple addition, a very simple extension of what we have been seeing so far can make the computational model quite powerful. This is actually same as having mod 6 gate also, that can be shown. Yeah. Suppose if you have mod 2 and mod 3, you can actually compute mod 6. So, ACC 06 can be computed using this. Whether this can be computed using ACC 06 is yeah, I think it should be, but of course, yeah, it can compute 12 also, but so yeah, so maybe this is a good question to think about. So, is ACC 06 equal ACC 0 2, 3. So, just think about this. So, yeah, so one direction is immediately clear, the other direction also should be possible. Right.
So, you can't infer as to if at all the sum would be 0 by 2.
So, yeah, so immediately you cannot infer, but then can you cleverly manipulate your input bits, or can you do some clever construction so that you are able to get this information from this circuit. So, that is the thing. No, 0 1. So, if it if it is, for example, if I consider ACC 06, if the sum is divisible by 6, it will output 0, otherwise 1.
Suppose input bits are x1 to x1 to xn, so we give say 3x1, 3x2, 3xn, and if at all it outputs 1, then the language is in ACC 0.
So also like 2, 3, this will
more equally powerful to all, like 12, 80.
Correct,
all
yeah,
factors that
right. So, yeah, if you have 2 comma 3, you can compute any linear combination of 2 and 3. Hmm? So, for 12 what you can do is, so you can do it for 6, okay, and then for 12 you again check it with another mod 2 gate. So, if it is divisible by so it should be divisible by 6.
You add 6 to it and again
2,
check with
3
6.
is more powerful.
You add 6 to it and then again check with 6. Mod p square can be done in p.
Any p to the power k can be done in mod p,
4 can be done in by 2.
right, but then how do you prove that any mod p to the power k can be done in mod p?
Because NCP, CP, NCP mod p and N mod p, that two consider.
There are 2,
If both of them are 0,
which 2?
N choose p and N choose p mod p and N mod p.
Okay.
So that if these both are they are not able to
Right. So, yeah, so think about it. I mean, I do not want to go into these details now, but I think it is a nice exercise to think these things. Yeah, so as you said, I mean, if you have a ACC 0 circuit with, let us say, p gates for some prime p, then you can compute the function mod p to the power k for any k using this kind of a thing. So, this is a more general thing to show, and once you show this, then you can easily show that 12, 18, all these things are possible, because 12 is nothing but 2 square and 3. So, let us look at communication complexity. Okay. So, what is the model and what are we trying to do here? So, the model in a communication complexity setting is very close to this interactive proof model that we saw, but well, I should not say very close, but it is kind of similar to this interactive proof model. So, there are two parties. Okay. So, there is a person, let us say, named Alice, and there is somebody called Bob. So, this is the traditional names that these communication complexity people use. So, the thing is that, so both these guys, they want to compute a function f. So, together they want to compute a function f. Okay. So, f is a function from 0 1 to the power n cross 0 1 to the power n to 0 1. Okay. So, in other words, f takes 2 strings, 2 n bit strings, and it outputs a single output bit. And what we assume is that Alice has the first string. So, Alice has, let us say, x, okay, and Bob has the second string. Okay. And as I said, the goal is to compute f of x comma y. So, what is f of x comma y? So, the entire input is not presented to both the parties. The first party gets one half of the input and the second party gets the other half. Okay. So, this is the main difference between the interactive proof model and the communication complexity model. So, in the interactive proof model, the input was visible to both the prover and the verifier. So, now the question is that how many bits needs to be communicated between these two parties, so that finally they are able to answer what f of x comma y is. Okay. And we always assume that both these parties have unlimited computational power. Okay. So, both Alice and Bob have unlimited computational power. Okay. So, let us look at some basic definitions first. So, let us say we have Alice and Bob. So, Alice has x and Bob has y. So, what Alice does is, so we define a protocol in the following manner. So, Alice computes the first bit. So, let us say Alice computes the first bit B1, which is applying some function P1 onto the string that he has, and he communicates this bit to Bob. Okay. So, now Bob can do the following. So, Bob applies some function P2 on his own string y together with the bit that Alice gave him, and let us say he gets some bit B2. So, I am just assuming here that these are single bits, but I mean they can be strings. Okay. So, it is possible that instead of one bit they compute a entire string. Okay. So, but let us just keep to this simple model, and he communicates this back to Alice, and then Alice computes B3, which is some P3 applied on x, his initially computed bit B1 and the bit that Bob gave him, and this gets sent to Bob, and so on. So, finally, Pt is I mean whatever it should be. I mean if t is odd, then Pt will be x comma B1 through Bt minus 1, and if t is even, then it will be y comma B1 to Bt minus 1, whatever it is. And the protocol actually ends, I mean it is a correct protocol if, so let us say that we denote this by pi. Call this our protocol. So, we say that pi is a correct protocol for the function if the last bit that whoever it is communicates, whether it is Alice or Bob, is equal to the value of whatever the function intended to compute. So, if I wrote this a bit incorrectly. So, Bt is Pt of whatever it is. If Bt is equal to f of x comma y. Okay. So, they do certain communications, and then the final bit is what the answer should be. So, now let us see what is the complexity of this protocol. So, what do you expect the complexity of this protocol to be? So, we define the complexity of this protocol to be the maximum over all choices of x comma y of the length of these strings b1, b2, so on till b t. Okay. So, for a protocol this is what its complexity is, and the complexity of a function, what do you expect this to? So, why do we take the max? It is because I mean it should be I mean we are looking at the worst case complexity. So, over all possible strings, whatever is the maximum number of bits that gets transmitted. So, now what do you expect the complexity of a function to be, the communication complexity? How would you define it? So, it is the minimum over all protocols pi of C of pi such that pi is a valid protocol for f. So, as many of you observed that trivial upper bound is n plus 1, because Alice can send x, sorry, it is an upper bound, because Alice sends x and Bob sends the answer. So, let us look at some specific examples. We will not get too much time today, but let us look at least one example. So, suppose we are looking at the following extension of the parity function. So, let us say I define parity of x comma y in the obvious manner. So, it is parity of x i's, I mean it is the sum of x i's plus the sum over y i's mod 2. So, can you design a clever protocol for this function? So, Alice has x, Bob has y, and they want to compute this. Okay, and then
one sends to the other returns the sum and mod
2 to be precise, right. So, exactly. So, Alice computes this quantity, he sends that bit to Bob, and then just Bob computes this quantity and takes the XOR with whatever Alice had sent and outputs that. So, this parity function has a communication complexity 2. So, let us look at another function. Okay, so, the second example is the most a more interesting example. So, this is the equality function. So, we say that this function evaluates to 1 if x is equal to y and 0 otherwise. So, now what is the complexity of this function, the communication complexity? So, what can be shown by simple counting techniques is that, so we will not discuss them today, but let me state the theorem is that the communication complexity of this function is lower bounded by n. So, no matter what protocol you choose, no, this is not obvious actually, I mean it seems obvious, but it is not so obvious, because what we are claiming here is that no matter what protocol we choose, we cannot do better than n. So, we need to transmit at least n bits back and forth. Not really, I mean we do not need any compressibility kind of thing over here. I mean we can just, and there are many ways to prove this, and if you just do some clever counting argument, you will be able to show this, and that is what we will do next time. But what I am trying to emphasize is that when we want to claim a lower bound, that basically should be over all possible protocols, and that is something which is I mean even though it seems obvious, it needs a proper proof. Okay. So, let us stop at this point, we will discuss the proof next time.